It's, last name is Stephanie. Your last name is Vo,
Yes.
just VO?
Yes.
It's not coming up. And the email is V.
It's stvo@umd.edu.
Oh,
I can also put that in the chat.
no. No. Okay.
I'll give everybody a minute to trickle in here, and then we'll get started in a minute or two.
Okay, I've sent it.
Okay, thank you.
Dave, do you have the roster pulled up for roll call, or do you want me to pull it up?
Let me see here. I have it in the list of the email guests. I have it here.
Well,
I can go down the list whenever you want, if you want.
So there'll be more people on the email list than are actually members. So I'm happy to run through what we have here, just going off our website.
Okay.
All right. We have one more minute. We still got a pretty good flow of people coming in.
Stephanie, did you receive? Have you received it?
I have not received your email. But you also, if it's not an issue for you, I think you are able to share your screen to present. It's not necessarily that I have to, but I'm happy to. I just haven't received the email yet.
Oh.
All righty. Well, I'm going to kick off roll call here, and we got a jam-packed agenda, and looking forward to it today. Bradley will not be joining us, so I will be actually doing my duties being chair and running this meeting today. All right. So with that, we'll start with roll call. Senator Ben Brooks.
Here.
All right. Delegate Mike Rogers. Not yet. So Secretary Designee, that's me. We have Evie Schwartz.
Here.
See you there. And then designee from Department of Natural Resources. So either Secretary Kurtz or Bob Szynski. All right, not yet. From the PSC, David Chai,
present.
Chai, sorry. Then have Diana Menendez. How about Pearl Donahue Villette? Already not yet. Dave Bugelmans, I saw you here.
Here.
Stacy Ono. Not here. Scott Elias. Oh, good. Thank you, Diana. And then Bob already is not here. All right. So I'm sure we'll have folks keep trickling in. So I'll keep an eye on the on our guest list as we go along here. First presentation that we're going to start off with today would be from Dr. Saleh Demisi. Did I say that
Yes.
right?
Correct.
All right. Speaking on solar recycling. So do you have your presentation sorted out? Do you want to try to share it? Or Stephanie, do you want to post it for
I
us?
don't know, Stephanie, if you have received it.
I did just receive it. Let me download it because I just a second before you said that I did receive the email. But yes, let me get that set up. And I will put that in presentation mode. Please let me know if you guys can
good.
see the presentation. Okay, great.
Thank you. All right, take it away.
Okay. Are we ready?
Yep, ready when you are.
Okay. Yeah. Oh. Okay. Good afternoon. Thank you for the invitation. I want to thank Mr. Baker for inviting me to share some of the work we are doing here at the US EPA related to solar panels, in addition to similar other related issues on clean technologies and material recycling and recoveries. So the outline of my talk would be I'll give you a general trends related to solar energy and solar panels, but then more focused on the model that we developed for the flow of the end of life of solar panels to help forecast how much of the scrap panels are coming in the coming years. And then towards the end, I will talk a little bit more about what are the drivers, the barriers for sustainable recycling or sustainable handling management of these panels. Next slide, please. So as you know, that the US has a mix of energy sources, from primary energy to based on fossil fuels to renewable energy sources. So in the past two decades or so, about 25 years, there is a rapid increase in energy transition, which is a global phenomenon, by the way, that from fossil-based to renewable energy sources. And US has a huge advantage to further growth of this energy, and there are various reasons for this. But what we see is that partly the US has a lot of open land and a lot of these resources, and the price of the cost of installing these panels or renewable energy sources has come down significantly in the past 2 decades. Next, please. So one of the driving force for behind this is thanks for the strong federal policies like the investment tax credits and state policies that give incentives for installing transition to renewable energy sources. But in addition to that, there is also the decline of costs. Right today, the utility cost for energy generation from solar panels is comparable to other sources. Actually, recent studies, from one study we saw that the cost of installing solar panel farms is almost the same as the cost of running a coal power plant. So there are economic drivers and also policy and also recognition of the benefits of solar panels, solar energy or renewable energy. So there is a change in public's perception about it. Now, next, please. So an example of this is that in 2010, solar panels contribute, or solar energy generation to the U.S. energy capacity was only about 4% of the total mix of energy of the various types of solar of the energy generation. But by 2020s, that has come to almost 50%. 43 to 50% of now of the new energy addition to the system comes from solar. So there's a huge surge in solar panel and solar energy installation, and as I said, there are lots of good reasons for this, and the price has come down. But as we need to remember is that solar panels have a certain lifetime of about 25 to 30 years, the current panels. So this we have to be aware that there is a growing concern now that this down the road there is a potential of scrap panels that needs to be handled. So this is in one side, it's a huge potential for recyclers, but also if we are not prepared, as this happened with electronic waste issues, that we might be caught that there's a large material that needs to be handled in a sustainable way. Next, please. So his article from BBC 2 years ago, it shows that our solar panels, an eco-disaster that's waiting to happen, or are there opportunities? So we are prepared for handling these panels and how to a sustainable way, that there is a big potential for recovering and recycling solar panels. But currently, only 10% of the PV panels are recycled. This is a study from the Renewable Energy Lab in NERL, the DOE study. But even in Europe, mainly the bulk materials are recycled, not all, because of partly cost issues. Okay, so next, please. So as a result of this, the US EPA and there are other sources also have studied that. We decided to study. So since solar panels have a reputation of being green technology, but the end-of-life management should also become to fulfill this promise. So we wanted to develop a model that projects the mass of end-of-life of solar panels by the next 10 to 20 years. So EPA Office of Research and Development developed methods to estimate the mass flow of and the composition of PV panels that becomes a scrap down the road in the next year by year, every 5 years. So this is helps to this kind of waste generation helps to inform federal, state, and local governments, recyclers, even landfill operators, and so that everyone, all the stakeholders have to be more informed how we can to develop a sustainable way of managing these products, this material. So next, please. So just a little bit of information on PV solar panels. So there are many PV models, hundreds of different types of solar panel models, but the main basic design is similar to the sandwich design of positively and negatively charged semiconductor materials that are sandwiched together, and most common ones which are monocrystalline and polycrystalline. Silica technology, which is about 80% of solar panels currently installed, contains aluminum and silicon are connected with silver wires. So multiple cells are then connected by a copper wire, which are soldered at the end with tin solder, and these are put together and glued with some polymer glue. and on the back side, what you see is it's another plastics polyethylene terephthalate. So the basic design is this. So it's all held by aluminum frame, and so the more robust, weatherproof it is, it's designed or manufactured, then it's difficult to dismantle and recycle, and that is one of the challenges that the longer the life you want from the panels, they become more difficult to recycle at the end of life. So they are not designed to be recycled. So the other issue is that the solar panel technology has evolved. Now we have second generation, which is different in composition, and third generation also panels are coming. So but all of them, they have a glass and plastics are the major components of this, and the materials that are recycled is right now are the basic, the frame, the aluminum, and the glass, and the others are not cost effective to recycle. Next, please. So, but that is not only the issue. What's also concerning us is that there are solar panels also contain small amounts of other heavy metals like cadmium and lead, and these are these are when they become a higher concentration, it becomes a health issue, a health and environmental safety issue. So, but so they have to be safely handled. But and the content and the composition has been changing over the years. Next, please. So, ultimately, what we want to do, we want to when you have a circular economy for recovering of these materials, and so in order to achieve that, we don't not only have we should not only are responsible for collecting solar panels and recovering material and achieving material recirculation to reach economic scale, but also we need to achieve we need to reduce the amount of material used and reuse and repair and maintain and extend the life of these panels. Sorry. Next, please. So now I'm talking more. I'll talk more about the model that we developed. So in the model that the guiding methodology for estimating model is for end of life of PV panels come from the International Renewable Energy Agency, so which they developed for different countries. And so now we took that model idea and used it for each state. So because we want to know how this differs by state, because the volume of installation of panels differs by state to state. So, but the basic idea is similar to what was used by ARENA for different countries. Next, please. Let me go to the slide. Sorry. So here is a basic methodology that we first determine the capacity of solar panels that are already installed for that state. So that comes from different sources of industrial, from the industry, the energy industry, and U.S. energy information, U.S. government agencies, and based on that we determine what fraction of that is from commercial and the other, and what fraction is on residential, and then we estimate the probability of losses of these. Is what is the expected lifetime and what is the loss, and I will talk a little bit more about that. And then from that we determine what is the expected lifetime, and then and determine so how long, when will they be decommissioned and become scrapped. So that is the methodology we followed for this estimation. Next, please. So the two factors here are important in the modeling is that what fraction of the panels are currently being installed in for residential sectors and what are in the commercial sectors. And this information comes, there's a rich information, detailed information by months and a year for each state and region. So we determined that and we only consider for this study in the grid panels. There are some panels that are small fraction that are off grid. The second part is that what is the expected PV life? What is the expected life of solar panels? By the way, that in the 1980s, the solar panels only have about 10 years to 15 years lifetime. Currently, in 2020, their average life is about 25 years. So for this study, we chose 30 years of lifetime, but that is critical because that's important to determine because that tells us when will they decommission become off the grid. Next, please. So there are the regular loss is 25 to 30 years, but then there are some early losses, and these early losses are caused by different reasons, and part of this is of damage or manufacturing issues and installation issues, and actually the industry calls this actually in the first 4 years. This is like infant mortality, that there is a portion of about 4% of them could be removed from early usage. And also there is some weather damage from the weather, hail, and sometimes hurricanes and similar weather incidents could cause this damage. So we use these two extremes of regular loss, early loss, and then from there in the middle is a midlife of to determine the flow of scrap panels. Okay, next please. Next please. So here is the calculations that of the steps that we followed. So in this modeling process, that the green boxes shows the process flow. The green boxes shows the data inputs for each step of the calculation, and the blue boxes shows the intermediate outputs. So we started with the in and out is the interface of the user interface. But once you select a state, then the other information behind what's the PV capacity, the market share between different sectors, the lifetime scenarios that will be calculated, and the weights also are estimated based on that. Next slide, please. So some general assumptions in this are we determine one a fixed lifetime for all different generations of panels. That is for the first step that we did, that may not be true, that but we used only a 30-year average lifetime, and that means based on that statistically that after 40 years none of them would, statistically there is very little of that installed will be in service. And there is about 2% of early loss broken during transportation, handling, installation, and some weather-related losses. So these are some basic assumptions used in developing the model, and they might cause some sensitivity to the estimate, but we will show you what it means in the results. Next, please. And the model, this is a function. The probability Weibull is a typical the probability distribution function that calculates the likelihood of solar panels lifetime, and the model can take many different shapes, but we use a two parameter model, one that explains the distribution of panel life. That's alpha, that the parameter determines the PV reliability studies of that factor come from different sources. And beta is, in this case, is actually the average lifetime of the panel. So if you go to the next. So here, the beta, the constant is the average lifetime, which is determined to be 30 years. So in the regular loss, we have three parameters here of the alpha, the shape of the probability function. Different parameters are selected. So basically, to determine that when does we start, what fraction of the installed panels come to end of life, and how long they serve, and when they will be removed from service. So next slide, please. And here is a typical example of regular life, middle life, and early life. So if there is a lot of panels removed from early life, that means the remaining, more the defective panels will be removed. So the remaining panels may serve longer than the average. But this is what it looks like, from the time they are installed, that when they come, when they come to end of life, and once they start passes at end of expected design life, then a lot of them will be starts failing and be taken out. Next, please. And so an example of this is, for example, because for this presentation I used at Maryland, there's quite a lot of information from different sources, and including solar panel installation, for example, over the past 10 years, based for residential, commercial, and other applications. It's a very steady, but there was some downward trends 6-7 years ago. It's coming back again, but at least it shows that it's quite energy information rich on details of panels and where they are installed, including locations of large panel farms. Next, please. So the market share information I got from we got from the U.S. Energy Information Administration, that contains a monthly cumulative installation and also yearly installation, both in commercial and residential. And the other information, next slide, please. The other information we get is a mass. Residential panels have a lower mass or a lower weight, are smaller than commercial, but these are all information that's fed into the model to predict, to come up with a number of how much of this will finally end up when they, how much scrap panels do we expect 20 years from now or 10 years from now. Next, please. So the interface, this is it. By the way, this model, this program is available for anyone to download and look at it. It's in our website. I'll provide you at the end. But it's it's a useful tool, and it gives you for the U.S. and for each state, including how much total mass, and also different for recyclers, how much silica, how much aluminum, how much of different components are could be collected from the scrap panels from that state. So that is a kind of user. It's Excel based model tool. Next, please. So what you see here is, for example, for the US, and I put the red arrow, or the horizontal arrow shows where we are today. It's relatively still low. So we expect from 200 to regular loss of about 36 to early loss of 500,000 of metric tons. But this could, what you see is that this is increasing exponentially in the next 25 years. So our estimate shows from 7 to 7.8 to 9 million metric tons by 2050. ARENA for the US expects from 7.5 to 10 million metric tons. But as you see is that compared to other total solid waste, and this is some people in the solid waste management might know more about this, you can have an estimate of that, compared to the rest of solid waste, this may be a smaller fraction, and definitely compared to other energy generation sources, it still is reasonably low. Next, please. So what you see here is that for the top states, is that 2030 is where it starts picking up. until 2030 we are okay, but then for all states there is a sharp increase in exponential increase, and the top blue curve shows you actually California, where we expect region 10, California in this case. So we are the highest installed and also the highest generator of these panels based on regular loss. RL means regular loss. Okay, next. So for Maryland, this is what the model estimates is that you can tell that it's compared to the top states, still is low, but also I have on the right side, so on the number, the data table shows you regular loss, mid loss, and early loss, and on the right, the plot shows a comparison of for the whole region 3, and it tells you that Maryland contributes about half of what region 3 to estimated loss. So it's considerably high for its size and population. Yeah. Next, please. And we put this actually, we contractor found this data, collected this. Where are these recyclers? If there is a recycling, and electronic waste recyclers may also are handling it, handle some of it, but where the recyclers are present, mostly in the West Coast and Midwest. And that is important actually for sustainable handling of these materials. Next, please. So there are still some things we need to tweak on the model, because it does not address some of the panels that are taken out of service, transboundary or internationally exported before they reach their end of life, and it does not include some of U.S. territories like Puerto Rico. And it does not address the different generations of panels. So the model has some limitations in that sense. Next, please. I have 2 more slides left. So I'll talk just in general that although the model gives us a good number to start with to understand what to expect, but the challenge is that part of the reason that a low level of recycling is because of the technical difficulties in recycling. So because these are not designed to recycle, and that needs to be more research needs to be done to achieve that. So, and there is also a need for infrastructure challenge. There is a need for a dedicated solar panel recyclers are very limited. We know of only 2 in the US. There's also other aspect is policy issues, and I think my colleague from the region, from program office will have some might say a few things about that. And but the bottom line is economic issues, because we need to demonstrate an economic benefits of PV panel recycling. So end of life solar panel recycling can effectively save a lot of virgin material mining, but that needs to be economically beneficial. Right now, it's much cheaper to just landfill than recycling panels. So that needs to the economy needs to be. Next, please. I have 2 slides left. So let me make just in general, policy and regulation the regulatory issues are important. So the policy importance is critical, and the states and local regulation differ by states. Like California have much more stringent take back programs, and Washington State have passed the extended producer responsibility. It's still not in practice, and a county in Niagara County in New York also. So these are some of the policy aspect is really important, and the US EPA currently is developing a new universal waste category for solar panels. Okay, I think that. So in conclusion, I want to say that the panel scrap flow is is increasing, and in the next 10 years, on past 2030, we will see a fast increase. But currently, there is no federal regulation exists, but there's universal waste rule is under development. California, Washington, Hawaii, Minnesota are developing also regulations to end-of-life management of solar panels. There is a need for R&D, research and development, education and information and training for a better sustainable stewardship of solar panels. So for more information, next slide, please. If you need, there's more in the EPA ORD website. You have more of these documents and tools that are available for anyone if you want to read more, and much more information in the ORD or DOE sites. Thank you for your attention.
All right. Thank you very much. That was a great presentation. And I know that people will ask, so I'm just going to ask up front, are we able to share your presentation after this so that people can take a harder look at it?
Oh, yeah, absolutely. And
There's a ton
also,
of information there, so it's going to be really helpful to be able to take a little deeper dive into the slides.
definitely, and I went through it very fast, and the background document for this, and including the model of you can take download and also play with it for different states, compare your state to other states. So all that is available for anyone to look at it more closely.
Thank you. And I see a ton of comments going back and forth in the chat, but rather than addressing all of the comments formally here, does anybody have any questions they want to bring up to the group right now? Or do we want to hold those a little bit later? But anybody?
Hey, Tyler, could we go to Phoebe real quick? Because I think she has an update, a very, very like 5-minute brief update about the universal waste rule making that EPA is undergoing. And then I think we can open up questions for EPA as a whole.
Sure, that's fine.
Great, thanks. Yeah, so I'm Phoebe O'Connor. I work in a different office from Sally, and I'm here today with my colleague, Kristen Fitzgerald. We're both in EPA's headquarters waste office, which is the Office of Resource Conservation and Recovery. Our branch works on RCRA generator and hazardous waste recycling regulations, and I'm the lead for our solar panel and lithium battery universal waste proposed rule. So I can give a quick background on universal waste in case there's anyone here who's not familiar with it. So the universal waste regulations are an alternative management pathway for hazardous waste under RCRA that are specifically designated either by EPA or by states. So they streamline the management standards compared to full RCRA Subtitle C hazardous waste regulations, including allowing waste to be stored up to a year and not requiring a manifest for shipping. And right now there's 5 federal universal waste categories, and we were petitioned back in November 2021 to add a solar panel universal waste category in light of, like Sally mentioned, there's some states that have already done this, California and Hawaii, I believe New York and North Carolina are also in the process of doing this. So we received this petition from I think 10 industry associations affiliated with the utility industry, including Edison Electric Institute, American Clean Power Association, Utility Solid Waste Activities Group, and some others. So what we've been hearing, and this is why they submitted this petition, is that folks have been experiencing a lot of difficulty in making a hazardous waste determination on solar panels at end of life due to how hard it is to get a representative sample from a solar panel, because like Sally mentioned, the parts, the heavy metals, in particular the lead, are distributed unevenly in the solar panel. So it's difficult to get a representative sample to perform the T-clip, which is a required test under RCRA, to figure out if a waste is a hazardous waste. So even though, as we understand it now, many solar panels are likely not hazardous at end of life, it's difficult to make that determination. So this is in part why the petitioners argued that universal waste would be an appropriate way to regulate solar panels, because it would provide an alternative management pathway that would make it easier to manage solar panels at end of life without the need to perform TCLIP. They also argue that it would increase recycling and decrease landfilling, improve regulatory clarity, and provide additional storage time for end-of-life management. And we evaluated the petition. We agreed with their reasoning. And in October of 2023, we started our work on the rule. So we met with our work group. We've gone through a lot of internal process here at EPA, and right now we're drafting the rule. And according to our schedule, which is publicly available in the Unified Regulatory Agenda, that has us proposing or publishing our proposed rule in June 2025, which at least for our team, we're still on track for that. But it's important to keep in mind that the election, either way it goes, could slow that down, because the rule has to go through the Office of Management and Budget. And when there's a transition, sometimes things can take a lot longer than they usually do. So I'll also add, like I mentioned early at the when I started talking, there's also a lithium battery portion of that rule. It's kind of outside of the focus of today's call, but if anyone has any questions about that too, I'd be happy to answer them.
All right, thank you very much. All right, now, anybody have any questions for our EPA folks? Going once, going twice. All right, well, with that, thank you guys so much for joining us. We really appreciate the presentations and all the information. We'll be anxiously awaiting June 2025 for the rule to be published. But we all know how regs go. It always takes a little bit longer than you hope for. All right, so on to our next agenda item. We have solar recycling and decommissioning capstone projects presented by David Comis. David, you still here with us? Yep, I see you there.
Can you hear me now?
Yes, yeah, ready when you are.
Good afternoon. My name is David Comis. While I work at the Maryland Energy Administration, I need to make it very clear that I'm not speaking for the Maryland Energy Administration. I'm simply reporting on the findings of 2 capstone classes at the University of Maryland Global Campus. 2 years ago, in my role as a solar program manager, I started looking at long-term recycling requirements for solar modules. Working with Dr. Sabrina Fu, Dr. Ken Seeley, and Master of Science in Environmental Management students from the University of Maryland Global Campus, we started considering factors that should be taken into consideration when siting a solar recycling plant in the Mid-Atlantic region, not necessarily in Maryland, Mid-Atlantic. To date, 2 capstone classes have been completed on this project. The Solar Energy Industries Association, which I will commonly call SEIA, is sponsoring a 3rd class that is ongoing even as we speak. When SEIA starts developing standards for solar module recertification, we may run 1 additional class to work with them on this process. Next slide. And next slide. Let me describe a couple of the study boundaries. We would only look at modules from commercial applications. We did not attempt to address the residential recycling problem. Commercial decommissionings deal with thousands of modules at a time, whereas residential decommissionings deal with tens of modules at a time. Nationally, about 80% of solar modules are used in commercial applications, but these numbers tend to be driven by the absolutely huge solar arrays in the Southwest desert. Until recently, Maryland was about 50% residential and 50% commercial. We're now 60-40 favoring commercial, and I believe we're going to be moving towards 70-30 over time. Secondly, we would only look at silicon-based solar modules as they comprise approximately 95% of the solar market. The company First Solar handles the recycling of almost all cadmium telluride solar modules across the United States. There is already a recycling process for those panels, so we should not see them in any waste stream that we see. As we started our project, it quickly became apparent that there are 4 potential options for solar modules that come offline: immediate reuse, recertification, repair, and full recycling back to base materials. This is true regardless of the module materials or the method of recycling. Next slide. Let's start with immediate reuse. With immediate reuse, modules are tested for operability and given a rudimentary visual inspection in the field. No repairs or replacement of parts is conducted. If the module passes both tests, it is segregated and sold as is, normally without a warranty. In most cases, the module will produce solar power at some value lower than its nameplate value. Immediate reuse from the field minimizes the transportation and the handling of the modules, leaving less chance for damage in the process. Used solar modules are better for smaller off-grid projects in rural areas, such as RVs or sheds, where the individual is going to perform the installation themselves. Typically, reliability is not critical in these types of projects. There are no tax credits for the purchase of the used modules. These used modules tend to sell at a very deep discount, typically 50 to 80% less than the cost of a comparable new module. At present, the market for immediate reuse modules is small and not well developed. Next slide. We're about to discuss module refurbishment and recertification, so I'm going to take a minute now to talk about various tests that may be used during the process. Initial testing is normally done while the modules are still operational in the field. The first test determines if all of the modules in a string of 10 to 20 modules are currently working correctly. A current versus voltage curve, commonly called an IV curve, is developed for the string. If the curve is typical, then all of the modules in the string are deemed to be operational. If the curve is abnormal, then the entire string is marked for further testing before disposition. Next slide. The red line shows a normal current versus voltage, an IV curve, for either a single module or for a string of modules. If the curve doesn't look like this, then one or more of the modules has a problem. Next slide. The second test is to search for hotspots on the modules while in operation. A hotspot typically indicates a point of high resistance and potential future failure. While this test can be done on a warehouse assembly line, typically drones equipped with infrared imagers are much more time efficient. Next slide. This graphic shows how a drone-borne imaging, infrared imaging can identify modules that may be damaged. They just stand out. You can see the green arrow on the slide on the left and the whole row of bad modules on the right, circled in green. Next slide. Once a module is removed from its racking, a cursory visual inspection is conducted to identify and segregate modules that have obvious major damage. These would be shipped directly to a recycling center. Modules that are not obviously damaged will go through an additional inspection, either in the field or at an intermediate warehouse or at a recycling center, depending on how the industry finally develops this process. The modules are normally cleaned. There's a wet process and a dry process. They're visually inspected, which can either be done by a person, or you take an image of it and you use a computer using AI to look. And the modules may be subject to additional testing. If a module fails any test, then a decision is made to either send it for repair or send it for recycling. Depending on the process being adopted, a sampling of the modules may be subjected to advanced stress testing. If the samples pass, the remaining modules of this group will not be subjected to additional tests. Complicating the process is the fact that the testing facility must be capable of working with many different sizes of solar modules. Non-standard size solar modules increase the testing and recycling costs, as the equipment must be designed and built to accommodate various sized modules. The bottom line is that sufficient testing should be done to provide whatever the required level of confidence is for the recertification that is being conducted. Next slide. This slide allows you to visualize exactly what I just said. We know that during the wear out period, that's the area in the blue on the right, the module failure rate begins to increase, but that's a statistical value. The purpose of recertification is to see if there are some combinations of tests conducted at the time of recertification, which presumably is at the point where the asterisk is on this slide, that if passed could provide high confidence to some additional number of years of reliable performance for the individual module. In other words, can we push the curve out to the right for a given individual module by giving it a series of tests which it passes? I asked NREL if they had an answer to this problem, and they said that they were applying for a grant to begin studying it. As such, I don't have an answer for you right now, and I don't think they have one yet either. This is one of the issues that SEIA must deal with as they develop standards for the refurbishment and recertification of solar modules. Next slide. For the purposes of this discussion, refurbishment takes an operational module, cleans it, inspects it, and tests it. Small changes may be made before testing to allow for additional longevity or to make changes required for safety. Refurbished modules may be assigned a new nameplate capacity reflecting the actual module output under standard operating conditions at that time. Banks and private lenders typically require proof that used modules have been tested and verified as operational. Hence, only solar modules that have gone through a refurbishment and or recertification process should be accepted. Unfortunately, though, insurance companies do not typically insure used solar modules. Typically, refurbished solar modules have a limited warranty of 1 to 5 years. The last question on this slide, is there a minimum capacity which recertification is inappropriate? Has a very subjective answer. It appears that modules with a capacity of less than 280 watts are no longer of interest in the secondary market, and as such may not be appropriate for refurbishment or recertification. I didn't put the number on this slide only because that number is going to change as the market changes. So whether it's 180 or 280 right now, it's going to change over time. Next slide. A repair takes a module that is not working and fixes it. Repairs are normally cost constrained, as it makes no sense to put $400 into the repair of a module that can only be sold for $200. Normally, repairs are confined to replacement of conductors, bypass diodes, junction boxes, and the installation of some backsheet repairs, normally with tape. These repairs are non-invasive and pose little risk to the environment and to the repair technicians. New laser and induction heating tools are being added to the repair toolbox, allowing for the reconnection and resoldering of certain internal wires without having to remove the glass cover or the EVA layer. While modules are tested after being repaired, there are no current standards indicating which tests must be performed in order to reuse the module. Repairs of older modules may be difficult to perform due to the lack of spare parts. Again, we're talking modules that were manufactured 25 years ago. Substitute parts may be required, in which case the module no longer meets the original manufacturer's specification. This could prevent the module from ever being used on the grid again. It is possible that codes and standards have changed since the time the solar module was conducted. Should repairs be required to bring the module up to the new standards? That's a question for SEIA to consider. Next slide. EPA showed this already, but just from top to bottom is the glass layer. Then the light blue is the EVA layer. EVA stands for ethylene vinyl acetate. It's a plastic. Then the solar cells, which is very, very wafer thin silicone. Then another layer of EVA, and then the backsheet. Next slide. Module recycling normally starts with stripping off all cabling. That's so we can recover the copper, removal of the frame to recover the aluminum, and removal of the junction box on the back of the module. At this point, the remaining portions of the module either go through a mechanical grinding process, a chemical dissolving and electrowinning process, or a hybrid process which combines elements of both mechanical and chemical processes. In essence, the mechanical process grinds up the entire module and attempts to recover the basic materials from the debris, specifically looking for aluminum, copper, glass, silicone, and silver. This process is currently used in Italy and other places and recovers about 90% of the module by weight. But if you notice the EPA slide, most of the value is in the silver. So the real question is, how much of the silver can you recover in order to go make it cost effective? The chemical process normally tries to remove the glass on the backsheet using a variety of mechanical processes, uses heat or burning to remove the EVA, and then uses a series of acid baths and electrowinning, which is essentially electrolysis, to recover the metals. In this way, almost all of the silver, lead, tin, and copper can be recovered. The EVA tends to be the big problem. It's very, very stable and tends to adhere to both the glass, the solar cells, and the backsheet. Removing it almost always breaks the wafer-thin silicone solar cells. It produces toxic gas when burned. While the Department of Energy has provided grants to universities to find a more environmentally friendly substitute, this isn't going to help for the current generation of solar modules and for those of the near future. There are some processes in research and development that may help with this EVA problem, but they are a few years out. Hopefully, they'll be available when a new recycling center comes online, and I'm going to talk to a couple of them right now. There is a supercritical CO2 delamination process that allows for full glass plate recovery. It removes the glass without damage, but it will damage the the silicon wafers. There's a solvothermal swelling with thermal decomposition, which helps recover the silicon. There's a new cryo milling, essentially freezing it and then milling it, with lead leaching and electrowinning, which is much better at recovering the lead in the other metals. There's a hot knife process to separate the silicon cells from the polymer encapsulant, then chemically extract the lead, silver, tin, and copper, which leaves the silicone. There's also, and this is my favorite, a microwave annealing process. Essentially put the panel into a big microwave that softens and separates the encapsulant from the glass and the cells. It still needs some considerable development, but this is also a way that would be able to go save the silicone. Now, also just to give a little bit of an idea, 1 megawatt of solar modules produces somewhere between 50 and 75 tons of PV waste, although most of that can be recycled to other uses. All of the aluminum, all of the copper, all the glass can be recycled, and that's more than 70% of the weight. However, this same 1 megawatt of solar modules only recovers 29 kilograms of silver and 16 kilograms of copper. On this slide, I've listed a number of factors that should be considered when siting a recycling plant. I want to address one aspect for special consideration. Depending on how the solar modules are characterized, certain states may limit the number of solar modules that may be stored on site due to the combined lead content. This could clearly limit the functions that occur at the recycling site. I'm sorry, next. Okay, we're already there. Now, where should the module inspection be done? Students looked at 3 basic options. The first option was to develop and deploy a mobile testing center, bring it to the site, and test the modules one by one as they're removed from their racking system. After testing, modules would be separated into the 4 piles. This process is being tried by one company on a small scale, but ultimately the students decided that the testing equipment would be too big and the throughput would be too slow to be practical. The second option was to develop warehouses and testing centers in areas close to where the solar modules would be decommissioned. This had the advantage of allowing for assembly line processing, the installation of heavy testing equipment, and allowing for precision equipment calibration. Now, we're talking about over $180,000 worth of testing equipment at a warehouse. It deserves to be protected and treated right. Under this option, the IV curve and thermal scans would occur in the field. Modules would be separated into 2 groups. Those damaged beyond repair, which would immediately be sent to a recycling center, and those which would be transported for further testing at the testing center. This facility would clean and refurbish the modules and have all of the required test equipment to recertify the modules. Once recertified and given a new nameplate capacity, the modules would be separated by size, manufacturer, and nameplate capacity. The testing equipment would be semi-permanent, allowing it to be moved to a new warehouse at a later date as the location of decommissioning is changed. Alternatively, more than one warehouse and testing center could be developed in the Mid-Atlantic region, allowing equipment to be permanently installed. One of the student groups made the recommendation to establish a repair center at the site of the recycling center, allowing modules that ultimately could not be fixed to immediately be recycled. Personally, and this is going to be my only personal comment in here, I disagree. There are limited cost-effective repairs that can be done to the solar module. The skill set is very similar to the work that may be needed for refurbishment and recertification. Therefore, the skill set should be available at the testing center. In addition, repaired modules can easily and quickly be sent back through the testing line for recertification. The final option was to send all modules to the recycling center, which would be built to have the capacity, the capabilities to both sort, repair, refurbish, recertify, and recycle solar modules basically from start to finish. This option minimizes the number of transportation cycles and allows all equipment to be permanently installed, but requires a large land footprint. Next slide. So now we need to ask, where are the modules coming from? When are they coming? And what percentage of the modules will be reused, refurbished, repaired, as opposed to recycled? And now these are the states that the students considered to be in the Mid-Atlantic region for this study. It's different than other definitions of Mid-Atlantic. Most manufacturers provide a 25-year performance guarantee for the modules. As such, 25 years is normally considered to be end of life for a solar module, but that's only based on the warranty. Modules at so-called end of life may still perform satisfactorily or could be repaired or refurbished. In some cases, solar arrays are repowered long before the 25-year nominal end of life. I've heard of some being repowered as early as 7 years after they were initially installed. These modules may be coming off the line with many years of reliable life ahead of them. Even modules at 25 years or more may have many years of reliable life ahead of them. If the workers decommissioning the solar array are properly trained and handle the modules with care, history shows that approximately 90% of the modules may still be reusable. Assuming that solar modules degrade 2% in the first year and about 0.4% for each year thereafter, a 25-year-old module would still be expected to produce at least 88% of its original power, and that's at the 25-year point. Next slide. This graphic and the next one were originally developed by students, but were not included in the final report. I felt that it provided important data for this task force, so I recreated it here. This graphic shows where and when the solar modules were installed. It only looks at arrays that were 300 kilowatts and larger. That's about 1,000 panels, 1,000 modules. I removed Washington, D.C., Delaware, and West Virginia from this graphic only because their levels were very low, and it simply added confusion to an already pretty busy chart. This shows that New Jersey, which is in the red, got out to an early lead, but North Carolina, which is in the dark blue, has had many years of large-scale installations and will likely be the first large-scale producer of decommissioned solar modules. Next up is Virginia, which is in the gray, with a blip in 2018 and a huge installation between 2019 and the present. Move this entire graphic out 25 years to the right, and you can estimate what will be coming down the line for reuse, refurbishment, and recycling. Next slide. However, and I used exactly the same vertical scale on this graphic, this is what recycling looks like if we are able to repair, refurbish, and reuse 70% of the modules for a second lifetime of only 15 years. As you can see, it pushes the major problem back until 2050, when new technologies may be available to address the EVA problem, allowing us to recover high purity silicon from the recycled modules. Next slide. Rail transport produces fewer module breakage than trucking by a factor of about 50. Trucking may be cheaper for short distances. For longer distances, rail is normally less expensive by a factor of about 4. With trucking, there are 2 transition operations, moving the modules into the truck at the decommissioning site and from the truck to the destination. With rail, there are at least 4 and sometimes 6 transition operations. 1 into the truck, from the truck to the train, from the train to the truck, from the truck to the destination. Rail is confined to fixed pathways of travel, whereas trucks are much more flexible on their origin, route, and destination. For short transportation distances, less than 150 miles, it may be more profitable for the decommissioning agent to own the trucks outright. For longer distances, hiring a third-party freight hauler is normally the low-cost option. By the way, that's based on a regulatory break at 150 miles, not necessarily simply looking at costs. Statistics show that between 2 and 5% of solar modules shipped with wooden pallets arrive at their destination damaged or in an unusable state. A shipping container, called PV pallet, costs about 100 times the cost of a single wooden pallet, but it reduces the breakage rate by 90% and can be used much longer than a wooden pallet, like 50 times longer. Wooden pallets can be used for other purposes at the point of destination and need not be returned to the decommissioning site. On the other hand, PV pallet is purpose-built for solar modules and must be returned to the decommissioning site for its next use. One final thought. Land in a rail corridor may be much cheaper than other land. As such, the location of a solar recycling center along a railroad corridor may be an advantage, and not just for the ease of transportation, but also for the low cost of land. Next slide. Next, I'd like to take a look at a couple of policy thoughts. The biggest issue, as it affects all transportation and transportation costs, is the designation of the solar module as either solid waste, universal waste, or hazardous waste. As we've just heard from EPA, they are working on a draft decision. At present, it costs about $2 to throw a solar module into a landfill and about $24 to recycle it. The only way to keep solar modules out of landfills is to prohibit disposal there. This will simply cause solar modules to be sent to other states without this restriction. So if we develop regulations, it must also restrict the interstate transportation of solar modules to new buyers or to refurbishment and recycling facilities in another state. The students identified the potential for the storage of a large number of solar modules on site. Some states limit the time and the number of modules that may be maintained on site. This decision is closely linked to the decision of how to treat the solar modules as waste. And until it becomes cost-effective to conduct solar module recycling, the states will have to establish a funding source to support the effort. This could be the module manufacturers themselves, the installers, the owners, or even society as a whole. Next slide. If we want solar modules to be reused, we could potentially consider offering an incentive to companies or to resellers offering product and installation warranties for the refurbished and reused modules. This would help to grow the secondary market. Until there's an acceptable and a totally accepted recertification standard, many states may continue to prevent reused and repaired solar modules from being used in projects that connect to the electric grid. As such, most reused modules will be used for standalone projects, which greatly restricts the size of this market. So we really need to go get the recertification standard out and accepted. Next slide. For the future, we need to reduce the number of modules damaged during decommissioning and transportation. There has to be value associated with the solar modules to motivate workers to take care of the modules. Now, this is probably 90% a training problem. In addition, industry needs to develop better but much less expensive shipping containers in which to transport the modules. To go along with this, we need to establish that processes that minimize the number of handling and transportation operations. At the present time, we do not know what the final recycling process and chemistry will be. With these studies and with this task force that we're on right now, we want to support getting to the right answer rather than be forced into the most expedient answer, because we simply ran out of time and didn't think about it. I recognize that ultimately this is a business decision of the recyclers, but the state can use financial and regulatory incentives to help bring possible solutions to market before the wave hits us. I'd also like to make one comment about the EPA slide that showed where the recycling centers are. Many of those recycling centers are small scale and cannot handle the numbers of solar modules that would be coming their way. So just because there's a blue dot on the screen doesn't necessarily mean that the capacity is there for what we need. Next slide. In closing, I'd like to acknowledge the students who devoted their capstone project studies to working on this project. Students and universities are assets to us if we're willing to use them. Unfortunately, 3 students are not listed here as we did not have their signed release forms, but there were 3 additional students. Next slide. As a reminder, these are the opinions of the students and not of the Maryland Energy Administration. This concludes my brief, and Dr. Fu, who is online, and I would be happy to address any questions you may have. Thank you.
All right. Thank you so much for that presentation. It's really nice to hear the students' perspective on this as well. I know a lot of research went behind all the points that they were making in the presentation there. I guess I want to kick off with my first question. I know you were making comments on the current capacity of recycling centers. You know, just because you see a blue dot, it doesn't mean that they're able to take all the waste that's being generated. Do you have any idea of what kind of capacity is out there for recycling right now, and like how much expansion do we need to be successful?
Honestly, I think Bob Nicholson is the best person to go answer that one.
All righty, Bob.
Hey, good afternoon, everybody. Can you hear me okay?
Yes, we can hear you now.
Great. So as many of you may know, SIA operates what we call a recycling partnership program, where we have a number of PV recyclers that we work with. The intention of the program, a bit to David's point about some of the recyclers on the map, the intention of our program is to identify companies that do have, 1, legitimate processing capability, and 2, have an appropriate capacity. So currently we have 12 recycling partners on our list that represent in excess of 10 million panels of recycling capacity per year. And we expect over the next 12 months, that list to nearly double and put us well into the mid 20 million range in annual capacity. I can also say that as the point person for that program, the number of companies now reaching out to me that are installing capacity or contemplating installing capacity is growing at an exponential rate. So we have a backlog of companies that wish to be partners that will be conducting the vetting process on. And then we have a secondary list of potential partners that we quite frankly just don't have the time to review at this point. So I can also say that right now, one of the biggest challenges for those recyclers is actually finding volume. So none of our recyclers are anywhere near capacity as they report to me anyways, and all are working very hard to find more volume to keep their process running.
That's interesting. And do you have an idea on, like, are we currently, like, the volume that we're experiencing, is it different than the volume that we were expecting in 24? Or do you think that we're gonna, you know, maybe in let's say 2030, map closer to where the desire is, or that, you know, I guess recycling capacity is?
Yeah, I think the volume just isn't there yet when you consider that 80% of all the panels deployed in the US today have been deployed in the last 7 years. So, you know, the industry has moved at lightning speed, getting technology deployed. And I think there's been a general belief that there's been an equivalent amount of panel waste coming out of the waste shed. I think what we're seeing right now is that's just not the case. And again, this is just what's reported to me from our recyclers, but their challenge is getting volume, and it's also somewhat slows the development of new recycling facilities because, I mean, everybody understands that it's hard to make capital investments for business that may not come to you for 5 to 10 years. So as we see these volumes tick up, I expect the recycling capacity to grow, at an equivalent rate.
Okay. It seems like I know you have a very good idea of the industry too. This is my last question. How, I guess, if you have 12 facilities that could have a 10 million panel per year capacity, how large are these facilities in order to do that kind of volume? Because everybody's processing, 800,000 panels. Are they doing it in a pretty concentrated area?
In most cases, the processing facility is surprisingly small. The space demand is really for storage. So as the EPA map pointed out, there's a concentration of recyclers from the Southwest across through Texas. They all have a significant amount of outdoor storage. So the actual processing floor, if you will, and the processing equipment, in relative terms, is a fairly small system. And many of our recyclers run the same type of technology. So, I've seen it in varying sizes of buildings, but it's not, as far as recycling facilities go, I would say it's probably a little less than average in size requirement.
Very interesting. Thank you. David?
Just as a comment, my study looked at a regional approach and not a state approach. But if you send everything to the recycling facility, whichever state gets the recycling facility gets all the jobs. If you break it up and you have warehouses that do the sorting, testing, recertification there, then you have split out a lot of where this laydown area is. But now you can do jobs in multiple locations. One of the reasons I mention this is because I know the Maryland Department of the Environment has been working with Allegheny County with a site that's along a rail corridor, makes it easy for shipment, and it's close to a lot of the off-takers for the recycling. That doesn't mean that we should necessarily do the recycling plant in Maryland. It's got advantages. As the students were looking, the initial load of solar is going to be coming from the Virginia, North Carolina area. And so the initial thought was to do at least a warehouse along the rail corridor in Southern Virginia. Just because of taxes and environmental studies and the cost of energy in those two states, which isn't in Maryland at all. So I just wanted to go say that even though obviously this task force is Maryland related, it's probably a regional problem in order to get the volumes that Bob just talked about in order to go support recycling. Because if we're able to do what we should do, 70% of the modules aren't going to come back for another 15 years. So we would be pushing out that big hump for a while. Thank you.
Yeah, not just as it relates to, solar panels, but as we look at like all these different recycling style programs across the board, one thing that I continue to talk to EPA about too is just the need for regional programs, because when you have smaller states like us next to larger states that have a lot more land mass, but we all have similar problems. We're passing similar laws with recycling in general. These regional approaches make it so much easier, and you can see that scale and you can see those efficiencies. So I think that makes a lot of sense too. Senator Brooks.
Yes, thanks, Tyler. Yeah, David, when you showed the panel about the IR testing, and then you showed the different modules in there that were bad, and right after that, there was the next slide was about the clean. It said you're cleaning and then visual inspection and whatnot. When cleaning, are you talking? Are you suggesting that solar panels should be cleaned periodically to enhance the amount of, I guess, the electrons is generating, or what?
In the field, there is a normal maintenance procedure depending on how much rainfall you get to try and clean the panels every 6 months or every year. But that's not what this was referring to. This is referring to after the panel has been removed from the field.
Mm-hmm.
The first thing that you would want to do is to clean up all the grime and grit and dirt and everything else as you put it through a refurbishment and recertification process to go maximize the amount of energy that the panel can produce, because you can lose somewhere between 1% and 4% just due to dust and dirt on the panel.
Oh, really?
So you want to clean it off at the warehouse before you start doing the rest of your testing.
I see. Okay. And also, you were talking about the some of the panels, the viability, I guess you'd say, of repairing, and whether or not you don't want to spend $400 on a panel that's going to sell for $250. So could one make an argument that in most cases it would be more viable just to go ahead and replace that particular panel as opposed to trying to repair it?
Most of the repairs, I'm speaking to it. Bob, do you want to address that one? If not, I'm just going to say as the students looked at it, there were very few repairs that made economic sense.
I see. Mm-hmm.
Having said that, with the new advent of the laser and the induction heating techniques, that may be able to go repair a number of the modules without having to take the glass and the EVA layer off, which is, since much of the damage of repairable cells is due to connectors that disconnect within the cell, that may allow you to be able to go fix those.
I see.
But it certainly isn't going to help for hail damage that breaks the glass or warped cells due to major windstorms or any of that stuff. They're all gone.
Right. I see.
Yeah. So basically, there's a very small subset of repairs that make economic sense right now.
Okay. All right. And thanks for telling me that the panels should be out in the field. It should be cleaned every 6 months to a year. I've got panels and I've never cleaned them. I'm hoping I'm getting enough rainfall.
But if you're in an area with rainfall and the panels are sloped at a slope, they will basically clean themselves for most of the dirt.
Oh, okay. All right. Thanks. Thanks very much. Okay.
Maybe Santa will do it for you in December too.
Yeah. Okay.
All righty. Any other questions from the group for David here? All right, Dr. Saleh.
Yeah, so I just want to add some of the comments to what Bob Nicholson and also David raised, to that overall, that there is a lot of study on extending the service life of the lifetime of PV panels. So this is also done by Department of Energy and NERO. So PV, it's possible to extend what their study shows, that it's possible to extend their lifetime from 10 to 20 years, and that really gives us time to improve the infrastructure and develop this the recycling potential for the different regions. So, so by doing so, this can be achieved by enhancing the PV reliability and improving some of the electronics that are critical gateways between the PV panels and the grid. But overall, that even when the panels are decommissioned, they are still about 80% efficiency of what originally installed. So, but there are currently studies on different scenarios of, is this by increasing their lifetime to 50 years, will that reduces the amount of raw material that needs to be making panels, and is how reliable and how feasible is that. So there are studies that show that it's possible to increase their lifetime by at least 10 to 20 years. Just want to.
Do these studies also show what tests need to be conducted at end of life in order to determine whether a solar module isn't going to fail the next day?
Well, I mean, I think that my understanding is that part of the reason that they are taking out is for not technical reasons, but also the warranty and there are the installation, so business issues. It could fail once it passes that time. That's the reliability of it becomes questionable. So, especially for utilities, large scale utilities. So that's an issue. But the test shows right now is that there are ways that components that needs can be replaced, and the improving the efficiency, the life of the overall life of the panels. So that and it's also selecting. I think they looked at different scenarios of, can we make these materials more better material selection through better material selection and sealing, reducing the weathering effect, so the aging. Can we make it last, make them last longer? So and it shows that it can be extended. But as you said, it's technically possible, but it could fail once they pass the expected lifetime.
All right. Any other questions? No? And also, members of the public, anybody have anything they want to ask or add to the conversation? Ed Hammerberg.
Hi, Tyler. Just if EPA is still on the line, I'm wondering if they could talk about the issue of whether solar panels from a residential setting are going to be considered household hazardous waste or not, or where they are in that decision.
Very interesting.
It's under review,
Well said.
under consideration.
As always, right?
Is that on the same timeline as the universal waste rule, or is that on its own decision path?
Yeah, no, it'll be part of the universal waste rulemaking.
Okay, thanks.
Sure.
Thank you. Good question. All right. Anyone else? Going once, going twice? All righty. With that, thank you so much, everybody, for joining us. We will have another jam-packed agenda next time. We'll be sending out an email in a couple weeks so you know what's going to be happening, what that agenda is going to be. But also another special thanks to everybody who presented today. A lot of great information. We'll make sure that those presentations are available online so that you can go back and review everything, so that you can take it in a little bit more than the rapid pace that we have to go through it here. So again, thanks everybody. I'll talk to you soon. Oh.
Hey, Tyler,
Okay.
real quick, Delegate Mike Rush, you did say you're going to send out the notes and everything to our email addresses.
Yes. Yep. And the recording will be made available for anybody who needs that too.
Okay. All right. Thank you so much.
Of course. Yeah. Have a good day, everybody.
All righty. Thanks, Tyler.